Hello and welcome to this video on what is a Heywood case. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level analysis, and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources including workshops that I offer through QuantFish. So in this video, I want to explain the term Heywood case in the context of factor analysis and structural equation modeling. So let's jump right in. What is a Heywood case? A Heywood case is also known as an improper solution. Improper solution means that you get results for your factor model or structural equation model. However, there is one or more parameter estimates in that output that is outside of the range of admissible values. As an example, variances logically can only be 0 or positive, and so when you obtain in an output a variance estimate that is negative, then this means you have obtained an improper solution or Heywood case. And this is actually something that happens quite frequently, in particular with regard to residual or error variances of latent variable indicators in a confirmatory factor analysis or a structural equation model. This is one of the more frequent examples, so to say, of a Heywood case is that one or more residual or error variances are negative, a negative residual variance. Another example would be a latent correlation that is greater than 1. So that can also happen in a structural equation model when you have two correlated factors or more correlated factors, then that one or more of those correlations is greater than 1 or smaller than -1, which is also outside of the range of admissible values for correlations. Correlations cannot be greater than 1 or smaller than -1. And so when you obtain an estimate that is outside of that range of admissible values, then that's an improper solution. So in summary, whenever you have an output where you have a negative variance or a correlation that is greater than 1 or smaller than -1, then this would qualify as a Heywood case. And so obviously that's not something that you want, because you wouldn't want to report a factor model or a structural equation model where one or more parameter estimates don't make sense, because how would you interpret that? You cannot really interpret a negative variance or a correlation above 1. Now, I'll talk a little bit more about the causes and the meaning of Heywood cases and what you can do about it as well, so that you can then make a decision about what to do with this. But in general, it means your solution as is you couldn't use. You couldn't report that. That would not be okay, so to say, to report a solution with one or more improper parameter estimates. So next, let's talk about what the reasons or causes are for Heywood cases. Why does this happen? And so there are essentially 3 possible causes of this. The most common cause is that your model is misspecified. Your model is wrong. So the model is either too complex, it has, for example, maybe too many parameters, too many factors, it overfits your data with parameters, and therefore some of these become improper. So variables, for example, become over-explained, or their variance becomes over-explained because there are too many factors, and then as a result you get a negative error variance, and that would then indicate that your model is overfit. Or the model may be underspecified. So it could also be the case that you don't have enough factors, and therefore the model is so misspecified that an improper solution occurs. So misspecification is probably the most common reason for this phenomenon, which means that in most cases you would have to think about revising your model to address this problem. Another, so the unrelated issue could be sample size problems. So when your sample size is too small for the complexity or size of your model, then those also occur more frequently. So all other things being equal, when you have a smaller sample size, you are more likely to run into Heywood cases than with larger samples. And this has to do or is related to the third most common cause of Heywood cases, and that is sampling error. Or you could say bad luck. So it can happen sometimes that simply due to random sampling fluctuations, you get a variance estimate that is negative, even though maybe your variance in reality in the population is maybe very small, maybe slightly positive, and then in your sample, due to sampling error, it turns out to be slightly negative. This can also happen, so it can be a sampling fluctuation problem. So then, what can you do about it? So how can you solve this problem when you run into it, when you run into an improper solution? What would you do about it? The first thing that I would recommend is that you take a close look at your model and that you think about in which ways this model may be misspecified. Is this model maybe overly complex? Does it have too many factors? For example, does it have method factors in addition to substantive factors, and maybe there are too many method factors, there are too many specific factors or something like that in the model, or maybe your model is underspecified. You could see that from fit indices, from the chi-square test of model fit, and maybe other fit statistics that would tell you this model does not fit the data, it is underspecified. And that's probably the most important thing to consider, is model misspecification. You could also ask an expert. Many people who are very familiar with confirmatory factor analysis or structural equation modeling, they could probably tell you right away by looking at the model and the output. They could tell you very quickly in which ways the model may be misspecified or in which way something may be wrong with the model. Now, the other potential reason for this problem was, or that I mentioned here, was sample size problem. So when you have a sample size that is too small, then Heywood cases are more likely to occur. And this is a problem, obviously, that you can resolve after the fact very easily when you have already collected your data, you've already fit your model, and you may not be able to collect another sample. And so what I recommend here is that before you even conduct the study, before you even collect data, you should run a simulation study to plan the sample size adequately. So you can run a so-called Monte Carlo simulation of your model, and you can specify the sample size that you are planning to collect to see if with a given sample size you have a high or low rate of Heywood cases. So for example, let's say you're planning to collect 200 cases and you're not sure whether an N of 200 is large enough for your factor model or SEM, then you can simulate that sample size across many replications, and then you can get a percentage or proportion of replications in which this model returned an improper solution. And so when you find, for example, that in 10 or 20% of those replications improper solutions occurred, then that may mean, oh, I might have to go a little higher with the sample size. So sample size planning via simulation is always a good idea when you plan a factor analysis or SEM study. I offer a free workshop on goquantfish.com on sample size planning via simulations. You can find the link for that workshop down below in the video description, so feel free to sign up for that workshop if you want to learn more about this. And then finally, in terms of random sampling fluctuations, that obviously is related to the sample size. So in order to avoid this problem, it is also a good idea to collect a large enough sample. Now, that being said, one approach that people sometimes take in the literature is that they will simply fix parameters that are improper to values that are admissible. So for example, when they find a negative residual variance for an indicator, they simply fix that variance to 0. Now, 0 is okay. Residual variance could be 0. That would indicate that 100% of the variance of this indicator is explained by the factors. So 100% reliability, so to say, or perfect reliability of that indicator, and then that addresses in a way this issue. However, I typically find that to be an ad hoc solution that I am not super happy with, because when you fix an error variance to 0, then it means you're assuming this indicator has perfect reliability, which is typically not plausible. And also, usually an improper solution indicates a deeper problem with your model or your analysis. And so simply fixing that parameter to be proper does not necessarily address the issue properly. So now sometimes you could say, okay, if it's clear that random sampling fluctuations led to the slightly negative variance estimate or a correlation that was slightly above 1 or something like that, if you find that plausible and say, well, this is really a sampling fluctuation problem, then this may be an adequate solution. But in many cases, it wouldn't be okay, because the problem would really point to your model being misspecified, and that is then something that you should address rather than simply fixing a parameter to a proper value. I hope you found this video useful to learn more about Heywood cases and factor analysis and structural equation modeling. If you did, then please consider subscribing to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.